All right, so it's an immense pleasure to introduce a friend of mine for many, many years, a great scientist and humanitarian, Mark Green, who is going to tell us about extension data for global limit mixed for structure. Mark?
Hi, so first of all, I just wanted to say how sorry I am not to be able to be at this conference. I just really am not able to travel right now. There are many very old friends of mine who I know are there, and also a lot of people I would like to meet. Certainly looking over the list of abstracts and so forth, there's just lots of work that relates to things that Philip and I have been very interested in over the years. And so I'm really sorry not to be there. I guess the other thing I'll say is that, so when I first got to UCLA and I was, a young, impatient person, I was sent an NSF proposal to referee. And after I'd refereed it, I happened to notice that the person who'd submitted it was 75. And I have to say that at the time I said, well, that's weird. But life is very ironic. And so this is the first talk I've given since my 75th birthday. It's okay. So the idea, so first of all, I should say that this work, all of it is joint with Philip. And then sort of the first part is joint with Colleen Robles. And then the part about pi1 is joint with Udmil. So global just means the parameter space is a quasi-projective variety, which we'll think of something smooth projective minus a normal crossing divisor. And there's a lot of, work on the local theory of degeneration of Hodge structure, where you parameterize by a product of punctured disks. And the interesting part is that doing things that are global gives you a little more information and makes certain things happen that I at least wouldn't have expected. So you have a variation of Hodge structure. I'm going to call Z sub capital I the intersection of the little component Z sub I, and the nilpotent part of the monodromy for Zi I'll denote by N sub I. And then sigma sub I will be the nilpotent cone for Z sub I. And so then we have the weight filtration and the Hodge filtration and the graded pieces of the weight filtration. So these graded pieces, of course, are quite interesting and essential, but there's extra information contained in the extension classes. And sometimes one kind of just neglects this, but in fact, it's got a lot of interesting information. And so that's what I'm going to talk about. So for example, if you have look at two adjacent graded pieces, they form an extension of mixed Hodge structure. And so the extension class is in this X1. And we'll call these the level 1 extension classes. And if we now look at a quotient of say Wm by Wm minus 3, then there are 3 graded pieces. And this, of course, has 2 level 1 extension classes between the M minus 2 and M minus 1 and the M minus 1 and the M. But on top of that, there's this level 2 extension class. And so although this is not an extension in an X2 in mixed Hodge structures, we don't have those, it is an interesting object nevertheless. And so of course you can do this for all levels and get level 3, level 4, et cetera. So I wanted to do an example, a very elementary example, to show that this is an interesting set of invariants. So if you just have an irreducible curve with delta nodes and X hat will be its desingularization, then we can think of this as being a degeneration of universal family. And then the graded pieces look like, well, there's a graded 0 piece that's a z delta, and a graded 2 piece that's a z delta of -1. The n sub i's map between these, and then the graded first piece is just h1 of the desingularization. So if we have the delta nodes of x naught, and we look at the 2 points pi, qi that map to zi, then the first extension class is in the Hom from h1 of x hat to z delta -1 modulo f naught of the Hom plus the integral Hom. And what this gives us is delta copies of the Jacobian of the desingularization x hat. And so this E1 contains the same information as sending the ith node to the integral from pi to qi of the holomorphic one forms. So this gives us a point in one copy of the Jacobian. There are delta copies of the Jacobian. Equivalently, of course, you can integrate the logarithmic differential with residues -1 and 1 at pi and qi over the loops of x hat. So those two things give you equivalent information. And of course, they're each have an ambiguity, which winds up being what maps you to the Jacobian, so for example, if you integrate it from pi to qi, you can change that by a loop, and then you get an integral period. So if gamma I is the path on x hat from pi to qi, then if I is different from j, you can integrate the logarithmic differential for pj and qj over gamma I. And so, of course, this has ambiguities. You can change the gamma I, and you can change by a loop, and you can change the eta by a holomorphic differential. But these are, of course, exactly these things that show up in the E1. And so what happens is, if you look at the exponential of this integral, it's in C star, it lives in a fibration over the place where the E1 data shows up. And it's this extra information that encodes E2. So of course, these integrals are very classical. Now, I'll say in a minute, I mean, of course, if you take I equal to j, you have trouble unless you add some extra information near pi and pj about how you're going to take this limit. And you can do that. But let me just say that sort of a wrinkle in general is that if you have local coordinates t sub I that define the z sub I, then the period map can be written as exponential of summation 1 over 2 pi I log ti ni times something in d check. But if you change your coordinates ti by constant, you change this point by exponential of a linear combination of the ni's. And so what is well defined, if you don't pick those normal coordinates or don't do something equivalent, you have to quotient by the action of exponential of the CNIs where I is in this capital I, the Z sub capital I we're on. Because these NIs are in the weight -2 part of endomorphisms, this does not affect the level 1 extension data, but it does affect the level 2 extension data. And exactly the I equals J case for curves is where you are losing this information, as you should. So you can put together all of this level 1 extension data into an element that E1 that's in the -1 graded piece of endomorphisms of Z, modulo the F naught of that and modulo the integral part. And I'm going to, for simplicity, just assume the weight filtration is defined over Z. And so this thing is a complex torus. And the graded pieces, I'm going to write just with an upper PQ. So P plus Q is -1. So F naught, of course, is where the P is bigger than 0. But the interesting part is now let U be the maximal sub-Hodge structure of this graded -1 that's contained in the -1, 0 plus the 0, -1 piece. So this is the middle of the Hodge decomposition of graded -1 of NV. And so if you have that, then you can, of course, make a complex torus out of this. And we'll see that often this J will have lots of polarizations, particularly coming from the NJs where J is, I'm sorry, now I made a mistake here too, J is not in I. Sorry. So the important observation really is that if you have a connected subvariety of Zi where the graded pieces are constant and the monodromy is trivial, then the level 1 extension data actually maps to a translate of this J. So you're landing in an object which usually is an abelian variety, but certainly is does not have, it's not like, doesn't look like an intermediate Jacobian would look. And there's a commutative diagram that, so this extends across any singularities. It factors through the Albanese map. So you have the Albanese map of Y, and then you just have what I'm calling a linear map of complex tori, just the obvious kind of map of complex tori that maps down to J. So this, of course, is very much using the fact we had a global family. So if this E1 is constant on Y, then you can arrange that the level 2 extension data maps, it's defined only on Y minus its intersection with any other ZJs. So Y star, I'm calling Y minus the union of all the ZJs that aren't in I. It maps to the graded -2 part of endomorphisms of V minus the F naught plus the integral stuff plus this direct sum of the C and I's that I mentioned. So if you look at the Hodge pieces of this, then P plus Q is -2. And again, F naught is the stuff where P is bigger to 0. And now the middle of this is the -1, -1 piece of graded -2. And let's let R be the maximal sub-Hodge structure of that. So just the Hodge, the -1, -1 Hodge classes in here. So notice that the stuff you write out by the C and I's lands is automatically in here. So then if E1 is constant on Y, then E2 maps, I'm sorry, this should be Y star and not Y, maps Y star to this RC modulo F naught RC plus the integral stuff plus the C and I's. And this is just a direct sum of C stars. So that's where E2 has to go if you had a global family. And then finally, if E2 is also constant on Y, then all of the higher extension data is constant. It's locally constant. So on a connected piece, it's constant. So in general, it sort of only can give you discrete additional data. If you just have a variation of mixed Hodge structure on a quasi-projective variety, and the monodromy is unipotent, then the same results will apply. So, okay, now I want to gradually. Well, transition to pi1, but I just want to check what I've got this. Yeah. Picture down here. Yeah. Let me, yeah. So if you look at the, you can put a weight filtration on the automorphisms of V by asking that Fp of V goes to Fp plus M of V for all P. And then the monodromy goes to W naught, and the action on the graded pieces goes to W naught mod W minus 1. And so if that's that on an irreducible component has a finite image, on a non-irreducible component it may not. And so if you take a finite cover, you can assume that action is trivial. And if it's trivial, then pi1 maps to this W minus 1 of ought V. Now, you can, basically this monodromy, you can think of it as looking like a nilpotent Lie algebra where you have identity maps on the diagonal, and then sort of the first piece of the monodromy is the first subdiagonal, and then the second subdiagonal, and so forth. And the information, the second diagonal transforms in a kind of way that's quadratic in the information in the first subdiagonal. The upshot is if you have this y and you take out the intersection with the zj's, so H1 of this looks like, has two pieces. The stuff coming from H1 of the complete variety and the stuff coming from the punctures. And they have weight -2 and -1. And as a result, the Albanese of y star, the thing that you get by integrating the one forms, including logarithmic one forms, maps to the Albanese of y, and the kernel is a collection of C stars. This Albanese of y star is a semi-abelian variety. And now the Albanese of y, as we mentioned, maps to J. And now H2 of J integral is wedge 2 of UZ star. H11 of J is the -1, 0 plus 0 minus 1 stuff, which is, well, tensored together. And now there's a natural bracket operation from the -1 graded piece of EV, wedge 2 of that to the -2 graded piece of endomorphisms of V. And that gives you, when the dust settles, a map from, I think it's RZ star, I'm not sure if I have the star right, to the Hodge classes, the 1-1 Hodge classes on J. And these are the Chern classes of line bundles on J. And that produces a fibration where a space S that maps down to J and has these C star fibers. Now, the content of some of our theorems, I sometimes call it the holographic principle, that in a way, there's this map to S given by the combination of level 1 and level 2 extension data. And the rest of the variation has only discrete data in addition to that. So this somehow is capturing all the continuous information. So just a little, I don't know, something probably unnecessary, that if you have a mixed Hodge structure with 3 graded pieces, and you look at the extension class of B over A and C over B, then the mixed Hodge structures with these 3 graded pieces is basically a fibration over these extension classes, and the fiber is this X1 mixed Hodge structure of CA. So you're getting this natural fibration. It's not an X2, which we know doesn't exist, but there's this vibration of X1s that does exist. And our Y, it's the complete Y, maps to J. The E1 extends across punctures. But up on Y star, you get a map which I'm calling E1-2, the combination of the information in the first two extension classes. And that maps to S, this vibration. And now E1, as we saw, factors through the map, the Albanese map. And the if you look at the fibers of the map to the Albanese, those are mapping to E2 information, these direct sum of C stars. And that map is given by integrating logarithmic differentials. In other words, it's given by information that's in the Albanese map for Y star. So basically, the information in E1-2 is finite over the fibers of that are finite over the fibers of the Albanese map for Y star. So now we're going to apply that to pi 1. So for the moment, I'm going to let X be quasi-projective. I'm going to eventually switch to having it be projective. But so if you look at the free Lie algebra on the first homology of X, then you can look at the Lie algebra you get by modding out by the image of the second cohomology. So over Q. So this is basically what John Morgan did, where here the map from H2 of X to wedge 2 of H1 of X, so the degree 2 part of this Lie algebra is dual to just the usual wedge product on cohomology. And so G is a direct sum from -1 to infinity of these G sub K, or if you, depending how you define things, you can put in a trivial degree 0 part.
Mark, I have a question or a comment. So
yes,
in this, the slide here is that one, yeah. So are you assuming that X is projective here? I mean, you've removed Z, but this, maybe I should see what you do with it, but this Lie algebra is not in general the correct Lie algebra for X. For example, if you took X to be C star bundle over an elliptic curve with non-trivial Schoen class, then this would not be the right Lie algebra.
so there, I think, and you're certainly more expert on this, there are two different ways of weighting things. One of which, I mean, when you have H1 of X, the way I'm doing things, I'm just calling all of that G1. But of course, some of it is, from a Hodge theory perspective, weight 2. And so when you look at this image of H2, then it has things of weights 2, 3, and 4. And
maybe I'll wait to see what you do with it.
Okay, so I'm going to restrict to the case where X is projective. So that's, I think, will certainly address your concern. So now we, following Dick, we construct a series of one forms for parameterized by G-1, G-2 inductively. And if X is compact, then we just take the holomorphic and anti-holomorphic forms to give us our omega minus 1. And now, to define omega minus 2, if you have something that is exact, that's a wedge product, that's a sum of wedge products of 1, 0 forms, then it has to be 0, and the same for the 0, 1 forms. But when you have a 1, 0 and a 0, 1 form, then it's D closed and D bar closed. So if it's exact, then it's the D bar of something. And we take omega minus 2 to be the 1, 0 form, in this case, minus 1/2 of df. So this gives us an omega minus 2. It's a 1, 0 form for every element of G minus 2. Then inductively, you can put all this together. At each step, what you want to do is to have the Morrow-Cartan equations hold. And inductively, you keep getting a closed form, which then, when it's exact, you can write it as a DD bar of something and keep going. And so in the end, you get something, a form, direct sum of all these minus j's that satisfies the Morrow-Cartan equations. D omega plus 1/2 bracket omega omega 0. So because this G is nilpotent, if you exponentiate, you have a Lie group associated to Lie algebra. And there's a converse to Morrow-Cartan, which Phillips says was proved by Cartan, that if you have an omega that satisfies Morrow-Cartan, and now I'm going to X tilde, the universal cover of X, then if you have a connected X tilde, so it's connected and simply connected, then there's a unique map to G whose derivative is omega, and which starts taking your base, whatever base point you've chosen, to E. And so in our case, this map is not holomorphic, but if there's a subgroup associated to the 0, 1 forms in X, and then X tilde maps to G mod H. And that is holomorphic. And now, so G itself, of course, has a natural Hodge filtration by the number of H10 of X's terms that are in there. And you get a map from pi1 of X tilde to G by taking gamma to this map psi of gamma X naught. And so the nilpotent completion of pi1 injects under this map, and it has a mixed Hodge structure, and the graded pieces are the GKs, but the extension data is varying as you vary X naught. And so this gives you a psi bar variation of Hodge structure as you move the base point. So if we add in a G naught that's Q, then basically the variation of Hodge structure, the E1, is just the Albanese map. And the map psi bar has finite fibers relative to E1. And so this then gives an alternate proof of the Shafarevich conjecture in this projective nilpotent case. So a comment is that although this extension data beyond level 2 only is adding discrete information, it still is extremely interesting. And the fact that it exists is important. So if you just had a Hodge-Tate variation of Hodge structure with quotients ZA of -2, ZB of -1, and ZA, then the period matrix would be if F2 would be of the form IAB, and for F1 of 0 IC. And I'm taking Q, the intersection pairing, to be this matrix here. So then what the Riemann-Hodge first Riemann-Hodge relation says is that C is the transpose of A, and that B plus B transpose is then A transpose A. But the infinitesimal period relation says that, well, this equation here, and then it says that DB has to be A transpose DA. It tells you, for example, that A transpose DA is closed. A is contributing level 2 extension data, and B in this case is contributing level 4 because you're switching between Z of -2 and Z of A, and Z of -1 and Z of A. So the existence of B forces this to be closed, and then of course you get into all the interesting iterated integral stuff when you look at these. So that's all I really prepared. So I guess we could take questions.
Yeah, hello, Mark. Can you comment a little bit on the quasi-projective case for the Shafarevich conjecture? What changes?
So sort of forgetting a little bit what we did, but you have to be a lot more careful with the DD bar lemma. That was the kind of when you start doing this Maurer-Cartan inverse Maurer-Cartan argument, and you start doing omega -1, etc., you start having to be more careful to keep being able to write things as D of something where you can then inductively define omega -2, omega -3, etc. So that's sort of what I remember at the moment.
Okay, thank you.
Other question. Small question, Mark, again.